In this video, you and I get to set up digital certificates in preparation for doing IKE v2 authentication using RSA signatures. Let's begin. Up to this point in our videos, we've been using IKE v2 authentication leveraging a pre-shared key. Now those keys themselves are kept, if we're doing it locally, in a local keyring on the router. And in the IKE v2 profile, that's where we identify that we want to do, based on the identity of the peer, where we want to do that pre-shared key authentication with them. However, there are some challenges with pre-shared keys. Number one, they're not as secure as other methods. For example, if we have digital certificates in place with PKI, and we can do digital signatures for authentication, that's much more secure than using pre-shared keys. It's also more scalable than using pre-shared keys. So I'd say that's our second issue. In this video, you and I are going to focus on the readiness or the preparation for getting digital certificates installed on R1 and all the spokes in preparation for using RSA signatures for the authentication of the IKE version 2 tunnels. Now, there are some prerequisites for this video that I'd like to go over with you. Number one, you should have already gone through CCNA security. So you've got a good understanding of the fundamentals of PKI and asymmetrical encryption. If it's been a while or if you haven't gone through it recently, I would strongly recommend you go back to this specific video in the CCNA security course right here at CBT Nuggets and watch the video on Crypto Essentials. And that'll be a good reminder about symmetrical versus asymmetrical and how public-private key pairs operate. I'm also going to ask you, in preparation for our PKI stuff that's coming up, to watch two videos from the CCNP Security VPN v2 course, also right here at CBT Nuggets. Those two videos are SSL and IPsec technologies and the video called Plugging into PKI. And to make sure that you and I are on the same page, let's go ahead and take a look at that course just for a moment. So here it is, CCNP Security version 2.0. Now, as you and I both know, the course that we're currently going through together is SIMOS, which is the Implementing Cisco Secure Mobility Solutions course, and Cisco has an associated cert number with that of 300-209. And what I want to point out is that virtually all of the content in CCNP Security VPN version 2.0 is directly applicable to this new certification. So if we scroll down a little bit, here are the two videos that I would like you to review as part of your personal studies as we begin to implement digital signatures in an iOS environment with IKE version 2. Now, you don't need to stop the video right now and just jump over to these two, because in this video, we're simply going to set up the routers R1, R2, R3, and R4 to work with a certificate authority, to authenticate with that certificate authority, which is a fancy way of saying get that certificate authority's digital certificate, so that we have the public key of that certificate authority. And then secondly, we're going to train our routers to enroll with that same certificate authority, and that will allow each of the routers to get their own individual identity certificate that can then be used as part of the digital signature process in authentication. So here's our game plan, my friend. We're going to go through this video together, and then what I'd like you to do is I'd like you to jump out and go to these two specific videos in the CCNP Security VPN course. And then once you've watched those two videos, our next video that we'll do together in this new course will be the actual implementation of the authentication using those digital certificates and digital signatures. Here's what you also deserve to know, and I'll share it with you right now about the CCNP Security VPN 2.0 course. The primary focus of this course is, of course, VPNs, specifically VPNs on the Adaptive Security Appliance. And virtually all of the videos in this VPN version 2.0 course apply to the new SIMOS. And here's why that matters. Later in this course, as we start approaching the ASA portion and VPNs and all their flavors on the ASA, I'm going to be referring you back to CCNP Security VPN for much of that content that hasn't changed between the two versions of CCNP Security. So if we scroll down this list of videos in this CCNP Security VPN course, let me share with you the ones that aren't going to be relevant for the new CCNP Security. I'm going to say you don't need to see the welcome video. And you don't need to worry about the old IPsec client because that's been discontinued. But everything else is relevant for the new CCNP security. And there's also a video that walks you through how you can emulate the ASA inside of GNS3. There's also another complete course on GNS3 if you want to do router emulation as well inside of GNS3. You may want to check out the GNS3 course. So even though I will be mentioning this again when we get to the VPNs portion for the ASA, I want to make sure that you know right now that the CCNP Security VPN course is a definite must-watch for a couple of reasons. Number one, if you want to learn how to implement IPsec VPNs on the ASA, that would be the number one reason to watch the CCNP Security VPN course. The second reason would be to troubleshoot VPNs on the ASA. And the third reason would be this number right here, 300-209, which is the Implementing Cisco Security Mobility Solutions Certification exam from Cisco that's part of the new CCNP Security. And all of these ASA-specific VPN videos, except for the intro, which isn't too critical, and the one video on IPsec remote access VPNs, all the rest directly apply and are required knowledge. So if you're creating a custom playlist, make sure you add CCNP Security VPN version 2.0 to your playlist. The main ingredients for PKI, the public key infrastructure, are certificate authorities. And I've got a certificate authority at 5.5.5.5 in my little virtualized internet. I'm going to use a Cisco IOS router to act as our certificate authority. The certificate authority is going to have its own digital certificate. Inside that digital certificate would be things such as the public key for that certificate authority, a validity date, and a serial number on that certificate. And what our routers are going to do, we're going to go ahead and ask the certificate authority if we can have a copy of that certificate authority's certificate. And they call that process authentication. We're going to authenticate the CA, which says, please, may I have a copy of your cert. Now, why would any device want a copy of the certificate authority's digital certificate? And the reason is we want the public key of that certificate authority. Because as we've learned in these videos, or as you will learn in those videos, as you go and review them again, is that the way that we verify a digital signature is we use the corresponding public key associated with that digital signature. Now R1, with a copy of the certificate authority's digital certificate, R1 needs his own identity certificate, and that's what enrolling is all about. When we enroll, R1 will previously have generated an RSA public-private key pair, and as part of the enrollment, R1 will send over the public key portion of that public-private key pair over to the certificate authority and say, hey, here's my public key, here's my identity, my IP address is this, my fully qualified domain name is that. May I please have my own identity digital certificate that contains a copy of my public key? And the approval process in the real PKI depends on the certificate authority that you're working with. And the certificate authority that's participating in PKI, it's going to do due diligence in verifying that the identity who's requesting this digital certificate is really who they say they are before they issue the certificate. So once R1 successfully enrolls and the certificate authority issues the identity certificate to R1, R1 can now use that digital certificate as part of the authentication of IKE version 2. Now, presuming that R1, 2, 3, and 4 have all authenticated the certificate authority, which means they all have a copy of that certificate authority's certificate, and they've all enrolled with that certificate authority, which means they now all have their own personal identity certificates, we would then configure the IKE v2 profiles to say we want to use RSA signatures for the authentication of IKE v2. So during the negotiations between R1 and R2, as an example, they are going to exchange digital certs. R1 will say to R2, here's a copy of mine. R2 will say to R1, here's a copy of mine. And one of the cool features in IKE version 2 is that if we want to, we can also specify a URL that R2 could go to get a copy of R1's digital cert, and vice versa. So the actual digital cert exchange doesn't have to be in the mix and part of the packets going back and forth in the IKE version 2 negotiation. However, traditionally, we're going to send those digital certificates back and forth directly to each other. Now, when these devices do exchange their digital certificates, how do they know that they're valid digital certificates? And the answer is R1 and R2 will both look at the signature. In this case, they're going to be signed by the common CA that both devices trust. And R2 and R1 can verify the signature of the CA because R1 and R2 have both authenticated with that same CA, and they both have a copy of the digital certificate of that CA, which includes the public key of that CA, which allows them to verify a digital signature of that same CA. So once these peers validate each other's certificates and consider them valid, they will extract the public key information for their peer. So R2 will have a copy of R1's public key and vice versa. And then in the digital signature process, as each of them use their respective private keys and digitally sign some data and send it over, The other party, using the sender's public key, will decrypt that and validate that, heck, that really is that peer. And that's one side of our authentication. That same process happens in the reverse direction with the other peer. And once the IKE v2 tunnel has been built and authenticated, then the child SAs can come up, specifically the IPsec SAs that can now carry traffic between R2 and R1. So in this video, we're going to do three basic things. Number one, we're going to set up a device on this little virtual internet at 5555 as a CA server. And then we'll have the other four routers authenticate with that CA server and then enroll with that CA server in preparation for the next video, where we'll have these devices use those digital certificates to do RSA signatures for the authentication of IKE v2. Now, to facilitate this inside of my little virtual cloud, I've got one single router with four interfaces, and it's R5 that's gluing the router 1, 2, 3, and 4 together. And on R5, let's go into configuration mode, and let's tell him that he can be an NTP master. We'll set the stratum to 5. Because one critical element in digital certificates is making sure that the time is agreeable on all the devices. So we're going to have this CA server, or R5, who's about to be a CA server, also act as an NTP server. Let's also create a loopback interface. We'll use interface loopback 0. We'll give it the IP address of 5.5.5.5 with a 32-bit mask, and that's going to be reachable by R1, 2, 3, and 4 as some device that's in that cloud between them. The simple certificate enrollment protocol, which is a very easy way to get certificates installed on Cisco routers, it does use HTTP. So if we want R5 to act as a CA server and participate as a server with HTTP, we need to enable that service on it. So we'll do an IP HTTP server here on R5. Next, let's create the CA server with the syntax crypto PKI server, and then you just give it a name. I'm going to call it capital CA. You could call it Bubba or John or whatever you wanted to name it. It's just a logical name for the CA service that's going to run on this router. Now, if we do a question mark here, there's a lot of options that we can specify regarding this router acting as a CA server. In a lab environment, we're going to keep it fairly simple and just put in a few of the parameters. And we'll allow the defaults for any parameters we don't specify to go ahead and be used. So one of the options is the hashing algorithm. So let's do hashing SHA-512. Also, because this is a lab environment, let's say that when anybody makes a request for its own identity certificate from R5, let's go ahead and tell it to automatically grant it without any manual intervention. So basically, R1, R2, R3, and R4, when they make their request using SCEP, the certificate authority, in this case R5, is just going to say, yeah, great, no problem, I'll give you the cert. In a production PKI environment, we'd want to validate that the identities who are requesting the certs really are who they say they are before we give them a digital certificate signing off that it's really them. And to bring this up, we're going to use the command no shutdown here in PKI server configuration mode. To protect the private key of the CA server, they want us to go ahead and put a password in. So I'm going to use a top secret password, and then I'm going to put it in again. It is done. You'll also notice it generated an RSA key pair in the background for its self-signed certificate. Now let's say, for example, that we're in an environment we didn't set up the CA server on a Cisco router, but we want to see the details of it. We can use the command show crypto PKI server. So in the output of show crypto PKI server, there's the mode auto. The last certificate issued was serial number 1, and that was the certificate for itself. And when a router acts as a CA server, you can actually tell it how much information to store regarding certs that it's issued. And the default, because we didn't set it, is minimum, which means no cert data is going to be written to any type of storage. So in a lab environment where we don't need that CA server to be up persistently, we're not going to be doing CRL checks later against it or anything else, this is perfectly fine. Next, let's make a road trip over to our good friend Mr. R1. Now on R1, before we start trying to authenticate R5 and enroll with R5, we probably ought to just verify basic connectivity to R5. So we'll do a ping over to 5555. That's a great start. Now that we know we have connectivity, we can now train R1 and configure the details regarding R5, who's going to be acting as the CA server. Because time is important, time keeps on slipping, slipping, slipping from my NTP. So we're going to do NTP server 5555 just because I want those clocks synchronized. And if we do that also on R2 and R3 and R4, then when R1 and R2 are exchanging certs with each other, or R3 and R4 are exchanging certs, when they look at those validity dates, the routers won't have any reason to think, hey, this cert isn't valid yet, or this cert has expired. If they'll have the same clock, we won't have any failures due to validity dates inside of the digital certificates. So the question might be, how do we know whether or not we've synchronized our time? We can issue the command show NTP associations, and that will help confirm our configuration. So we've got 555 configured as a server. Another command that we can issue is show NTP status, and that's another way to help us verify that our clock is synchronized. So in the output of show NTP status, it says, sure enough, clock is synchronized. And that is great news. Now, a big part of enrolling with the certificate authority is having the public-private key pair already generated. And part of that enrollment is going to be sending up our public key information, asking the certificate authority to help put that into a digital certificate, which the CA server can sign and then issue to R1. So we don't want to put the cart too far in front of the horse. Let's create a RSA public-private key pair right here on R1. We'll use a modulus of 2048, and we'll give this key pair a name. We're going to name it r1.cbtnuggets.com. You could name that key pair Bubba or John or whatever you'd like. It's just a label that's locally referenceable by this router for that key pair. So here's our syntax: crypto key generate RSA modulus 2048, and then the label. It took 8 seconds for that to crank it out. And because we now have an RSA public-private key pair, it also enabled SSH support. 199 means that this router is capable of handling SSH version 1 or SSH version 2. If we want to see our public key information, we can use the command show crypto key mypub key RSA, and then if you want to put the actual label that we labeled that key with, we can add that as well. If we didn't add the label, it would just show us all of our public key information. So the output reflects that the key name is r1.cbtnuggets.com, because that's what we named it. They are RSA keys. They are general purpose keys, which means we could use them for encryption or for digital signatures as part of authentication. And here's our public key information. Now the trick is we need to get that public key inside of a digital certificate that's signed by a trusted CA in order for peers like R1 and R2 to do authentication with RSA signatures. So our next step is to identify the certificate authority that R1 should go ahead and trust. And the syntax is crypto PKI trust point, and then we just give it a name. It's only a locally significant name from R1's perspective. Some details that R1 desperately needs to know about this new certificate authority that we're identifying here is, what is the IP address that we'd use for enrollments and authentication with the CA? We're going to specify that as enrollment URL http:// and the IP address of R5. We've already verified we have basic ICMP connectivity with the ping, and because we enabled the HTTP service as well on R5, that URL should then work. We can also specify from R1's perspective which key pair that's currently sitting on R1 we're going to use during the enrollment process. So if we have 5 or 6 different key pairs, we could identify based on the label which one we want to use. As an example, let's specify RSA key pair and the label for that RSA key pair that we just created, the r1.cbtnuggets.com. So when we created the key pair, if we just called it Bubba, we would just call it Bubba right there as well. Now regarding the ingredients that we want to go into the digital certificate once we enroll with the CA, we can specify that as well. For example, if we wanted to include the fully qualified domain name of r1.cbtnuggets.com, we'd say FQDN, and then that fully qualified domain name. If we wanted to specify x.500 information, for example, the subject, we could add that as well. So in this example, subject name, common name equals R1, organization is cbtnuggets.com. And that information is going to be put as part of the identity certificate that R1 is going to get from that certificate authority server once it enrolls. Our certificate authority server doesn't have a whole bunch of information regarding certificate revocation lists as far as revoked certificates. So on the client, I'm going to specify that with this CA, revocation-check none, which means don't bother regarding certificates received from this certificate authority. Don't bother doing a CRL check, a certificate revocation list check. So with digital certificates, if we received a digital cert and we wanted to validate that it was correct, we'd check the signature from the CA, we'd check the validity dates. We could also check the certificate revocation list just to verify that it hasn't been since revoked from that CA. In our lab environment, we're not going to do any revocation checking. And then we'll exit out of trust point configuration mode. Next is the magic. If we want to go ahead and authenticate that certificate authority, which means we are asking for a copy of that certificate authority's digital certificate. We're not asking for our own identity certificate. We want a copy of that certificate authority certificate. They call that in Cisco authenticating the CA. And to do that, we're going to use the syntax crypto PKI authenticate, and then the name of the certificate authority that we just identified. In this case, that's trusted-CA. So we've contacted that CA, and we have this MD5 and SHA-1 fingerprint. And if we wanted to verify that, is this really the CA that we think it is, we could make an out-of-band request, for example, a phone call to the certificate authority and ask them to verify the MD5 or SHA-1 hash. And we want them to read that to us. And that's how we could verify out-of-band through a phone call that we are talking to the correct certificate authority that we think we are. And do we want to accept it? I'm going to type in yes. So now we have a copy of the certificate authority's digital certificate, which has a copy of the public key for that CA, sitting on R1. So if we wanted to verify our work, we could do a show crypto PKI trust points. We only have one, trusted-CA. So we want to verify the configuration. This command would do it. And also check this out. It's also showing us that the certificate is configured, meaning we've got it. So there's the URL. It added this part automatically for us, because all we put in was this URL, and it added the port 80 and the /CGI-bin. So we know we have the certificate from the certificate authority, but if we want to see that certificate, we can do a show crypto PKI certificates, and that will show us that certificate and details about that certificate. So that's the serial number that the CA gave itself for its own self-signed certificate. The issuer of the certificate authority CA was himself, so the issuer CA, and the validity dates are all the way through 2017 regarding that certificate authority certificate. And from R1's perspective, this trust point, which is a fancy way of saying this CA, is named trusted-CA. So now that R1 knows who the CA is, we've authenticated that CA, so we have a copy of that CA's digital certificate. The next thing we want to do is we want to go ahead and enroll with that certificate authority, which is effectively requesting our own identity certificate, which contains our public key. So to do that, we're going to use the syntax crypto PKI enroll and the name of our trust point, the name of our CA that we've just configured and authenticated. So we haven't received our identity certificate yet, but we're warming up to the idea. It's asking us, hey, please put in a password that in the event in the future you ever need to go ahead and request a revocation of this identity cert that we're about to issue you, you'll need to make sure you have that password for us to process that for you. So I'm going to put in a password, and I'm going to repeat that password. This information right here is going to take and put into our digital certificate, and that's because we specified what the fully qualified domain name was, and we specified the organization name and the subject name as part of identifying that trusted CA. And now it's asking us, do we want to include the serial number of the router as part of the digital certificate? And I'm going to say to that, no, I don't really care about the serial number of this specific router. Do we want to include the IP address in the subject name? Now in this case, it's R1, and if we do want to include the IP address of R1, if it's a static address, for example, we could say yes to that, and then put in the IP address of 15.0.0.1, or the interface name, which would then be associated with the IP address that would be fed up as part of our enrollment to get our identity certificate. And then finally saying, okay, I've got all the information I need. Do you want to request your own identity certificate from the certificate authority? And I'm going to type in YES and press enter. And automatically, because we have the certificate authority set up to grant auto, meaning to automatically take that request, take the public key, take the information, create the digital certificate for the client, and then send it back, we now have our own identity certificate installed on this local router. So we have two certificates. We have the roots certificate, which has the roots public key, and we have our own identity certificate with our, in this case, R1's public key. Now it's telling us that we can issue the command show crypto PKI certificate verbose trusted-CA, and that's going to show us a lot of information about the certificates that we have, including the fingerprints, if we ever need to go back and verify those. So regarding certificates, we should have at least a couple. If we look at this first one, it was issued by CA, which is our CA server. The subject information for our identity certificate, the name is r1.cbtnuggets.com, IP address is 15.0.0.1, the common name is R1, the organization name is cbtnuggets.com. Here's our validity dates. Here's the fingerprints associated, or the hash values, if you will, associated with our identity certificate. It's X.509 version 3. If we scroll down a little bit further, it'll also have the information regarding the certificate authority's certificate, which is, so we have the issuer is CA and the subject is CA. And if we put more details on the certificate authority, it could have included more information in the subject name for its own digital certificate as well. So the great news is that R1 is ready to go as far as infrastructure. It's got a copy of the CA certificate with its public key. It's got a copy of its own identity certificate with its own public key. And of course, R1 also has, but not part of the digital certificate, it has its own private key that's associated with the public key that's in the digital certificate. So our next step is to configure R2. So let's make a road trip over to R2, and we'll do this a little bit quicker because it's the same exact steps. And by telling R2 that we want to use the same NTP server, we're just playing it safe by making sure that our clocks are all synchronized. In a production environment, it's also a great idea to validate that NTP is synchronized before certificate authority enrollment requests. And a big reason for that is if we make a request and it's sending back to us our identity certificate, R2 is going to check the signature of the CA server, which he can now verify because R2 is going to have a copy of the public key of that server. If we're doing certificate revocation checks, we might check the CRL. And there's actually more than just one method to verify whether or not the certificate that was issued by a certificate authority has been revoked. We could actually download a certificate revocation list, or we could use OCSP, which stands for the Online Certificate Status Protocol, which is another method for letting us check to see whether or not a certificate is still valid. And then third, we're going to go ahead and check the dates, the validity dates for that certificate. And if R2's clock thinks it's 1987, and the cert says it's good from 2014 to 2017, R2 is going to say, wait, that certificate's not even valid. So the NTP is just a great idea. Next, let's generate a public-private key pair for good old Mr. R2. We'll use a 2048 modulus as well, and we'll label this RSA key pair as r2.cbtnuggets.com. So the basic syntax is crypto key generate RSA, and then the other options are just that, they are options. And it says that took about 9 seconds to complete, which is fantastic. Next, we're going to tell Mr. R2 about the Trusted Certificate Authority. We'll name it Trusted-CA with crypto PKI trust point, and the name of that certificate authority. We'll specify the enrollment URL, the RSA key pair, based on the label we gave it that we want to use as part of that enrollment coming up, the fully qualified domain name for Mr. R2, and we'll also include the subject name information regarding R2 and the organization that R2 is a part of. And we're also going to say we're going to skip any type of revocation checks. Next, we need to go ahead and authenticate with that certificate authority so we can download and have a copy of that certificate authority's digital certificate. So if we want to verify the fingerprint out of band with a phone call, we could. And the second step would be to go ahead and enroll with that same certificate authority. And the syntax is crypto PKI enroll and the name of our trust point. I'll specify a password and confirm that password. And that password would come in really handy if we had to go to the certificate authority and revoke, for whatever reason, an identity certificate that they had previously given to us. So I'll say no to the serial number, yes to the IP address. This is R2, so its address is 25.0.0.2. And request certificate, I'm going to say yes. And we now have our own identity certificate installed. So if we want to verify our certificates, we can use the command show crypto PKI certificates, and it'll show us all the certificates we have installed, which are going to include on this router at the moment the certificate for the CA server and our identity certificate. Now this process of identifying the certificate authority by setting up the trust point on the local router, and then authenticating with that certificate authority, and the enrolling with that certificate authority is going to be identical on R3 and R4. So I will do those additional 2 routers off camera because the syntax is going to be identical to what we've already seen on R1 and on R2. I have had a lot of fun. Of course, my recommendation would be to practice everything we've done together in this video. And to assist with that, in the Nugget Lab files associated with this course, there's a document called Setting Up Digital Certs and a CA. And it has all the steps, including setting up R5 as a certificate authority, and then for R1, 2, 3, and 4, all the exact steps for them to set up time synchronization with R5 and then authenticate and enroll for their own identity certificates with R5 acting as the CA server. I have had a great time. I am so glad you joined me for this video. I hope this has been informative for you, and I'd like to thank you for viewing.